everyone. I'm Xinyu Yao. I'm a PhD student in Information System and Management at CMU High College. It's my great pleasure to share my research. All right, let's get started. The reason we study the resource allocation problem for patient care is that there has been increasing operational conundrums in healthcare system. These issues lead us to think about, can we model and solve resource allocation and sequence assignment problem under stochastic setting to improve patient care management? Importantly, we need to consider the capacity of heterogeneous resources serving multiple groups of patients, and each patient requires multiple consecutive care activities. Each activity has a random distribution depending on their type and trajectory. And our specific objective is to minimize this expected total waiting time for all scheduled patients. Fortunately, the recent emergence of the real-time location system provides a great opportunity for us to solve the problem. Based on the data, this work managed to solve the problem with the following approaches, and our solution conquers some common issues in the previous work. They use time index and rank-based formulations, which are intractable in the large-scale setting in our case. And then let's move to the model details. First, I would like to emphasize the details of our model objective. We aim to allocate and design different types of resources, including physicians, staff, and equipment, to sequential activities of all scheduled patients to satisfy their clinical care requirements. We need to determine three parts of decisions. The first one is which individual resources will serve which patient care activity. The second part is the activity sequence assignment from the perspective of individual resources. The third is the exact start time of each activity. The objective of the model is to minimize the expected total waiting time for all patients. This slide shows the entire formulation of the two-stage stochastic model. I just skipped the deterministic one. We just put the constraints related to the random durations into the second stage and put the ones without the randomness in the first stage. And the first stage is optimized in terms of the expected total weighting over the duration distributions, while the second stage is optimized given the first stage solution and the further duration information. After we formulate this model, we encounter another problem that it is intractable to find the exact solution for computing the expectation requires complicated multi-dimensional integrals. We cannot deal with the entire random distribution or the entire scenario set. So we need to think about methods that can approximate the stochastic program with a smaller set of scenarios. And the sample average approximation is the exact method we want. And we transform the two-stage model to the SA formulation. You can see that they use a similar constraints, but SA has index n, which means that the duration is a function of the scenario. For each scenario, there will be a sample duration realization, and we use the equal weights for each scenario. And here, as the sample size increase, the assay solution will be closer to the optimal, but it will hurt the computation efficiency again. Therefore, we need to use the Monte Carlo Optimization approach to find a small n, but can still get a near optimal solution. The MCO start from trying a small sample size and goes on the iteration till reaching the stop criteria. And here is the model integration summary for the experiments. Based on the real-time location data, we generate trajectory instance, and then we solve the baseline model whose first stage is solved by the deterministic model with duration mean. And next, we run the stochastic model where the MCO helps find the sample size for each instance, while the assay formulation is used to solve the problem. And finally, we compare the stochastic model solution with the mean value baseline. The metric we use to compare the two models is the estimator of the value of the stochastic solution. The VSS, it measures the expected gain from solving the stochastic model rather than its deterministic correspondence. And next, we move to the experiments and results section. The data of the experiments is collected from the orthopedic clinics. We carry out the data processing to find the patient resource interaction trajectory. After getting all the trajectory, we select the top 5 and to figure out the final dominant trajectories. And then we feed the log normal distribution over the activities durations as well. And then based on the data exploration, we run experiments with parameter settings over the number of patients, arrival sequence, and patients' arrival interval in the number of bottleneck resources. We visualize a complete result in the following slides. We can see that though the computation times grows naturally as the complexity of the model grows, and more congested settings requires more computation time, but we can still get a good near optimal solution for the complicated models, which is necessary for the actual clinical settings within a reasonable time. And then the VSS and ratio plot show that our stochastic model achieves significant improvement in total waiting time compared to the deterministic post baseline, and the VSS and the ratio improves significantly as number of the patients considered in the model increases. The total waiting time can be reduced by around 60% on average for the most complicated scenarios.